Take a deep breath. There are about 50 sextillion atoms in every breath that you breathe in. That's a 5, followed by 22 zeros. 7 octillion atoms make up your body. That's a 7, followed by 27 zeros. The whole of planet Earth is composed of 100 quindecillion atoms, or a 1, followed by 50 zeros. In the entire observable universe, 46 billion light-years across, there are thought to be up to 100,000 quadrillion vigintillion atoms, or a 1, followed by 82 zeros. And the biggest number in the cosmos can actually be arrived at by dividing the total volume of the observable universe by the smallest possible unit of volume, the Planck space. Dividing everything we can see into minuscule cubes, we end up with 1 times 10 to the power of 185 of those cubes. And yet that is not yet the biggest number that humans have conceived. Take, for example, the Goliath that is Tree 3. As Antonio Padilla, physicist at Nottingham University, puts it, everything you think you know is dwarfed into nothing. Welcome to the game of trees. You start with a coloured seed, which can give rise to a tree whose branches end in seeds that can sprout their own trees. The goal is to make as many trees as possible, and there are 2 main rules. The first tree must contain 1 seed, the second a maximum of 2 seeds, the third a maximum of 3 seeds, and so on. At each level, the tree can contain less than the maximum number, but that maximum is fixed to correspond to the level you're at. Secondly, the game ends and the forest dies if you create a tree that already exists within the forest. So if you repeat a pattern of coloured seeds that are linked together, no matter how far away it is in the forest, it is game over. Mathematicians have played this game with different numbers of seed colours. Tree 1 allows only a single seed colour, and the forest dies at the first tree. The second seed you add is necessarily a repeat of the first. Tree 2 can last up to 3 trees. Starting with 1 colour, you make a tree that contains 2 branches, both of a second colour. The next tree has just 1 branch. By the next step, all possible combinations of 2 colours have already been used, and you can't avoid building a tree that's already been seen. But then you come to Tree 3. Tree 3 uses 3 colours, and Tree 3 is different. Whereas the previous forests died disappointingly quickly, a forest of 3 coloured seeds grows for an extraordinarily long time. Mathematicians have proved the game must end at some point, but they've not been able to count the trees it would take to get there. They've not been able to, because if they did, their brains would implode. As Antonio Padilla goes on to say in his exploration of huge numbers, for a while you feel nothing untoward, a string of digits growing larger and larger in your mind's eye. And then it happens. Just trying to imagine a number that large is more than the human brain can take. Trying to hold that number of digits in your head would result in a black hole forming from the sheer quantity of information crammed inside. Indeed, faced with all the digits of Tree 3, scientists believe that the entire observable universe will also suffer the same fate. And so, the solution to Tree 3 is, without a doubt, a mind-bendingly enormous number. But it is still a finite number, and so it is still smaller than infinity. In fact, however big the solution to Tree 3 is, it is much, much closer to 0 than it is to infinity. Whereas counting to the top of Tree 3 may be a foolish thing to attempt, it isn't futile, because there is an end. But infinity has no end. It just keeps going, without reprieve. For every digit, every object, every anything, no matter how large, there is another waiting in line, and another, and another. So, what happens when you keep going? Is the universe itself infinite? And what would it mean to live in a universe that never ended? Take a deep breath. Things are about to get weird. Albert Einstein once said that politics is more difficult than physics. Ground News have kindly supported this video, and they are the world's first news comparison platform. Because though Einstein was exaggerating a little, discovering the truth behind what you're reading has become much more difficult since Einstein's time. We are constantly bombarded by misinformation and news with a specific agenda, especially online. Ground News is the solution to clickbait news. They make it easy to swipe between headlines to discover which details are emphasized, exaggerated, or left out entirely. The app has become an essential tool for me and one that I've been using for a while now. As someone who believes in objectivity and critical thinking, I find it a lifesaver when finding the truth behind a story. They have great tools like the factuality score, bias distribution, and media ownership data, so you can find out who is behind your news. You can even have it scan your Twitter or Reddit feed to find out your own bias. So, if you're looking for a better way to stay informed about current events around the world, check out Ground News by visiting ground.news/HOTU. Thanks to Ground News for supporting education on YouTube. Around 530 BC, in the small town of Croton in southern Italy, a secretive band of brothers meets in a lamplit room, whispering in hushed tones while they wait for their illustrious leader to make his appearance. Their conversation is impassioned and reverential, like that of any cult, but these men do not speak of gods. Their concern is with the human soul, with geometry, and above all else, with numbers. As their master emerges from the shadows, his disciples fall silent to better hear his latest doctrine. For everything that the great Pythagoras utters must be the absolute truth. In ancient Greece, it wasn't uncommon for scholars and their students to worship philosophical and mathematical concepts, but the Pythagoreans took things to a new level. Believing in the transmigration of the human soul into the bodies of animals, followers were strictly forbidden to eat meat. As such, the cult were thought to be among the first ever vegetarians, although this would have been a challenge, as they believed a small part of a man's soul was lost every time he passed gas. Pythagoras preached that the only escape from this endless cycle of death and animalistic reincarnation was to seek higher knowledge of the universe. And so, the Pythagoreans built a doctrine around numbers. In their reverence of the rational, the Pythagoreans sought to support their worldview by demonstrating the utility of the counting numbers 1, 2, 3, 4, and so on. Whereas unwieldy, ungraspable, irrational numbers were evil, defined by darkness and maleficence. In the cosmic battle of light over darkness, that which was unlimited was to be abhorred and avoided at all costs. But it was in geometry that the Pythagorean doctrine began to crumble. The closer they looked, the more they realized that not everything could be explained so simply. When attempting to calculate the length of a square's diagonal, there was no neat and tidy solution that equated it to a ratio of two counting numbers. The result was always irrational, always inelegant, perpetually troubling. The one thing that carried Pythagoras' name down through the centuries, the calculation of diagonals in squares and triangles, is the very thing that caused his cult such discomfort. Irrational numbers were an unavoidable part of our reality, however disturbing that was, and among all numbers none was more disturbing than infinity. Over the coming centuries, philosophers who were not so rigid in their mathematical doctrine as the Pythagoreans began to contemplate the concept of the truly limitless. Take, for example, Zeno's paradox, named for another ancient Greek. Picture any journey you must complete, like the journey home after a long day at work. In order to go home, you must first travel half the way there. Then, to cover the remaining distance, you first have to travel half of it, bringing you 3/4 of the way home. Traveling half of the next stretch completes 7/8 of the journey, and the next half brings you 15/16 of the way home. Following this principle of splitting each stretch of the journey into halves, you can continue traveling halves an infinite number of times and never reach your destination. This situation wouldn't happen in reality, of course. You would make it home after work eventually, but there is no doubting the logic of these infinite divisions. Many Greeks tried to reconcile this by relegating concepts of the infinite to the divine and metaphysical, claiming that they weren't a part of the rational world. However, others tried to categorize infinities themselves. There was a difference, they claimed, between an actual infinity, which is an infinite quantity of things that exist all at once, and a potential infinity, which only comes into existence as a result of a process. So, counting to infinity, or subdividing a journey an infinite number of times, are potential infinities, whereas actual infinities, like an infinitely large object, were still despised and refuted. They were simply impossible. Some 2,500 years have since passed since this ancient introspection, and with it has come waves of mathematical and scholarly advancement. No longer tied to cults or secret societies, numbers could be analyzed for what they really were, rather than what they signified. And the same was true for our ideas of infinity, marked by a huge leap forward in the late 19th century by a German mathematician named Georg Cantor. Cantor was the first to consider that there truly are different kinds of infinity. He described how there are an infinite number of counting numbers, but also an infinite number of even numbers too. Both groups are infinite in size, despite the fact that the list of counting numbers completely contains the list of even numbers, plus the odd numbers as well. This apparent paradox is possible purely because of the bizarre nature of infinity. Each of the even numbers can be put in a numbered list, paired with a corresponding counting number. So, 2 is number 1, 4 is number 2, 6 is number 3, and so on. Right up to infinity. You'll always be able to match an even number to a counting number. So, they are both the same size. But Cantor also showed that there are actually infinities of different sizes when you consider subsets within an infinite number of counting numbers. Take the 4 members of the Beatles, John, Paul, George, and Ringo. How many different combinations or subsets of members could you form from among this group? You could have each of the 4 by themselves, pairs like John and Ringo, or Paul and George, trios like John, Paul, and Ringo, and you can have a set of 0, no Beatles at all. In total, there are 16 possible configurations of the 4 Beatles, many more than the original number, and the same applies to infinity. Because of this multiplying nature of subsets, there will always be more subsets than there are counting numbers. There are indeed infinite sets of infinite counting numbers, but one infinity is necessarily larger than the other. If you find this to be twisting your brain to breaking point, you're not alone. Georg Cantor himself suffered several nervous breakdowns over the course of his career and spent the last year of his life in a mental hospital. Nevertheless, we must continue to consider the infinite if we hope to understand the past, present, and future of the cosmos. For all their complexity, Cantor's transfinite mathematics and the Greeks' desperate reasoning with impossible paradoxes were limited to the contemplation of numbers alone. The Greeks desperately tried to avoid any contact between the infinite and reality, but astronomers now find themselves confronted with actual infinities at every turn. From the infinite densities at the heart of supermassive black holes to the potentially infinite expanse of the universe as a whole, scientists are now equipped with the mathematical and practical tools to tackle these problems head-on and face the many oddities of an infinite cosmos and what they would mean for our tiny, fleeting existence. A young man surveys his home with wary eyes as he pushes through the undergrowth on North Sentinel Island. Brushing his hand lightly across the leaves as he passes, he recognizes each of the trees, bushes, and craggy rocks. They are as familiar as the faces of his children. Gradually, the trees thin and open out to a sandy beach, beyond which is a vast expanse of blue. He knows this land, this beach. He's even fished from his boat in the shallow waters not far from shore. But the ocean extends far further than the shallow canoe will ever be able to carry him. It plunges to dark and unfathomable depths, and it stretches out and encircles his island with a solid halo of blue. This is the man's entire universe. The island is his world, and everything he can see is all there is. And yet, one afternoon, when he and his companions are bringing in the day's meager catch, something new arrives in the man's universe. It's a white speck, at first too small to make out at the edge of the ocean. It gradually grows in size as it approaches the island, and before long it casts its long shadow into the fishing waters. The young man and his brothers are justifiably terrified of these new alien beings that have descended silently into their world. They throw rocks and sticks at the gigantic vessel before retreating back under the cover of trees. Had the Sentinelese man been focused on anything other than repelling the immediate danger, a flicker of curiosity may have come to him. If the island and its ringing ocean was all there was, then where did these aliens and their giant vessel come from? If he had peered back out from the safety of the trees at the end of the day, he would have seen the white boat shrink and then disappear beyond the horizon of the man's own universe. Was there a vast expanse that lay beyond his own observable cosmos? Scientists and philosophers have long grappled with the concept of an observable universe and what, if anything, lies beyond. As early as the 4th century BC, the Greek scholar Archytas considered what it would be like to travel to the edge of the heavens and then extend his hand out beyond the limit. There could be nothing greater than the heavens themselves, and so this, he claimed, clearly implied a space without limit, an essentially infinite universe. In the 16th century, Italian philosopher Giordano Bruno also concluded that space was infinite and contained infinitely many things, a statement that, unfortunately for him, angered the church. Bruno was captured, tortured, and eventually burnt at the stake. Never had contemplating infinity been so mortally dangerous. And so, in the following century, the English philosopher Thomas Hobbes came to a much more acceptable conclusion on the nature of the infinite universe. It was meaningless to speculate, he said, whether there is or is not an infinite cosmos beyond what we can see, because there's simply nothing we can do to measure it. Better to put the idea to bed and concern ourselves with the many mysteries that we can see, rather than those we never will. Whether through self-preservation or genuine conviction, his assertions have echoed down through the centuries and are still repeated by scientists to this day. Why speculate when nothing good can come of it? Although you're unlikely to lose your life over the matter these days, you may still lose your mind. Nevertheless, a few brave cosmologists still choose to risk befuddlement in tackling the potentially unknowable. Today, we have better tools than ever to probe the observable universe and centuries of science, mathematics, and philosophy to cling on to as we contemplate the potentially infinite reality of what lies beyond. Like the tribes of North Sentinel Island, our view of the cosmos is limited by how far we can see within it. Light never travels faster than about 300 million meters per second, and so the further we look in space, the further we are looking back in time. We can see galaxies from 1 billion years ago, from 5 billion years ago, even from 10 billion years ago. But at a certain distance, the light fades away. We see no more galaxies, because this long ago, there were not yet any galaxies to be seen. The edge of our observable universe is therefore defined as much by time as it is by space. It is not a physical construct, just a measurement of how fast light can travel. And the distance to that edge is further defined by the expansion that has taken place since those first galaxies started growing. Their light has been traveling for 13.8 billion years, so they are at least 13.8 billion light-years away. But in the intervening period, space has continued to expand, and so those first galaxies are now some 46 billion light-years distant. Though when we probe the limits of our observable universe, it is very clear just how little the edges look like edges. There is nothing in the structure or distribution of these distant galaxies to suggest they're all piled up against an invisible barrier. Even though it is vanishingly unlikely that the cosmos began with a perfectly even distribution of matter and energy, on the broadest scale, that is what we see. There is no center to the universe. On scales above about 230 light-years, wherever we look, there are no places that are any hotter, colder, or more or less densely clustered with galaxies than anywhere else. Using the cosmic microwave background, a universe-wide afterglow from just 300,000 years after the Big Bang, affectionately known as the universe's baby picture, scientists have found differences on the largest scales of barely a couple of parts in 100,000. In fact, this homogeneity is considered strong evidence for the cosmological period of inflation, a fraction of a second at the beginning of time when the universe is believed to have doubled in size some 80 times, thus expanding away many of its smaller wrinkles. And so, by taking inflation and its resulting homogeneity into account, despite the vastness of a universe 92 billion light-years in diameter, it really must be much, much larger if it is to contain the inevitable irregularities of the early universe. As Thomas Hobbes said, though, there is nothing we can do to probe that distant expanse, and no amount of modern technology will change that. We are forever limited by the speed of light. But we do have an almost infinite capacity for imagination. And meaningless or not, we can speculate about exactly what lies beyond. In general, there is still an overarching aversion to the concept of an infinite universe, and cosmologists are doing all they can to find a mechanism that puts limits on the amount of stuff out there. But how can you build a finite universe without invoking something beyond? How can there be limits without an edge? For that, there is at least one potential explanation. If a Sentinelese tribesman were to take his canoe out into the unforgiving open ocean, beyond the horizon and onto the great blue sea, he could travel for years without ever reaching a precipice. With favourable winds and currents, he would eventually find himself back at North Sentinel Island, having fully circled the globe, but without ever having reached an edge. Just as the 2D surface of the Earth is finite without edges, because it curves back on itself, so cosmologists suggest that the 3D universe is also curved, and is similarly limited without margins. And this is something we can actually test. On any flat surface, two lines that start out parallel to one another always remain so. They never touch and they never diverge. On a positively curved surface, like the surface of the Earth, lines that start off parallel will eventually converge and touch one another. And on a negatively curved surface, like on a saddle, then parallel lines will gradually diverge, moving further and further apart. In the 1930s, Edwin Hubble attempted to apply this reasoning to the three-dimensional universe by counting the number of galaxies he could see along a certain sightline, recording how that number changed with distance. It seems like a sensible approach, but in reality, the universe is not so simple. As we look to greater distances within the cosmos, we look back in time, and the inevitable evolution of galaxies through time is sure to have an effect on the counts at different distances. But there are other ways of investigating the same geometric principle, using more standard and predictable features of the universe. The explosion in cosmological science since the 1990s has equipped astronomers with their best tools yet to try to probe the unknowable vastness of the universe beyond our grasp. Using so-called standard candles and standard rulers, made up respectively of intensely bright supernovae and sound waves from the early universe frozen in place by the formation of atoms, astronomers compare their models of the shape of the universe with what we actually observe in the skies. Powerful space telescopes like WMAP, the Wilkinson Microwave Anisotropy Probe, have measured the precise mass of all the matter and energy in the universe and compared it with critical masses that would result in eternal expansion or inevitable contraction. We've even probed the tiny irregularities in the cosmic microwave background in search of any hint of curvature. Either a positively or negatively curved spacetime would give limits to the ultimate size of the cosmos. Even a complex surface of positive and negative curvature in different directions could help define the edgeless boundaries of a finite universe. But when cosmologists actually make these measurements, they are consistently finding a troubling pattern. As far as we can tell, regardless of where we look or how we look, the universe appears to be flat. It extends off in all directions, with no hint of hill or valley. Does that mean it goes on forever? At first glance, it certainly seems so. But then again, at first glance, the ocean seems flat, extending out endlessly in every direction. If we could just get another perspective, say by soaring higher than the average passenger plane, we would be able to see that same ocean curve around. It has a positive curvature that our surface-bound eyes can simply not resolve. And scientists are similarly limited by the resolution of their instruments. There are plenty of technical challenges to observing distant cosmic phenomena from our planet, and our very best observations are only accurate to a precision of 1 in 400. That means that while the universe may be flat as far as we can see, perhaps we aren't soaring high enough to get the full picture. But at the very least, the flatness we've observed so far puts a lower limit on the size of the unobservable universe. For it to be curved and yet still look flat, it must be at least 37 trillion light-years in diameter. It is an immense distance, some 1,000 times larger than our observable bubble. But that is just the smallest it can be. It could be much, much bigger. It could be infinite. On the 15th of August 1977, a volunteer astronomer was reviewing pages of data from the Big Ear radio telescope at Ohio State University when he saw something that made him stop in his tracks. In the days before widespread computer processing, the observatory recorded and printed out the signals it received every 12 seconds, indicating increasing strength with first the numbers 0 to 9 and then letters of the alphabet, A to Z. So when Jerry Amon saw the sequence 6EQUJ5, he was actually seeing a distinctive spike in radio noise, a spike larger than anything the telescope had seen before. Knowing what such a narrow and isolated beep from the sky could mean, he circled the characters and wrote "Wow" alongside. And to this day, the isolated radio scream is known as the wow signal. At the time, Big Ear was tasked with listening for signals from alien civilizations as part of the growing search for extraterrestrial intelligence, known as SETI. Scientists had no good idea of what a message from the stars might sound like, but they knew it must be clearly distinct from the usual sounds of space, which was exactly what Amon spotted. The wow signal was loud, never repeated, and couldn't be traced to any visible phenomena in the night sky. Was this our first and only indication of alien life in our galaxy? To this day, the signal remains a mystery, though most scientists think it's more likely that the pulse of radio waves came from a natural, rather than alien-made source. But even if the wow signal turned out to be a cosmic fluke, one of the odd quirks of an infinite universe is that aliens would most definitely be real. Microbes, little green men, even vast, galaxy-devouring monsters. Simply put, in an infinite universe, not only is everything possible, everything is. Attempting to filter this vague statement through a scientific lens, the physicist Sean Carroll suggests that there are 4 options. Number 1, the universe is finite in size and finite in time. Number 2, the universe is infinite in size, but finite in time. Number 3, the universe could be finite in space, but last forever. And number 4, perhaps most bafflingly, the universe could be both infinite in size and infinite in time. To start with, let us consider a universe of infinite size and finite time. This universe must surely contain endless nothing. But just as there are infinite even numbers and infinite counting numbers, there can be infinite emptiness and infinite structure, all at the same time. That in itself is enough to confuse, but the true oddness begins when considering what exactly makes up that infinite structure. Considering first the phenomena that we can already observe, things like stars, galaxies, planets, and life, these would be among the objects that presumably would exist in infinite numbers across a cosmos of infinite size. This means that there would be infinite configurations of stars, galaxies, planets, and living beings out there, more than we can ever hope to count, chart, or travel to. Even if, by some small possibility, the only life that exists in the observable universe is on one small rocky planet around a 4.5 billion-year-old yellow star, then this alone is enough to make the list of phenomena that must be repeated ad infinitum throughout the cosmos. Indeed, there must be an infinite number of clones of each and every one of us, each contemplating their own place in the eternal universe, and infinite variations. Cosmologist Max Tegmark estimates that they would be something like 10 to the power of 118 meters away from us. Factoring in the possibility of an infinite number of different phenomena, things become even weirder. Literally anything you can imagine, and an infinite number of other things beyond, could be happening, must be happening in the universe at any given time. Indeed, quantum mechanics means that anything within the known laws of physics is possible at any time, though many of these possibilities are, statistically, incredibly unlikely. But this is no impediment to a universe of infinite size. From cups falling through solid tables to entire galaxies appearing and disappearing in the blink of an eye, anything, everything, and all in between would populate this zoo of oddities. And again, just as with Cantor's even and counting numbers, all possibilities would happen an infinite number of times, no matter their statistical likelihood. And in a universe of finite size but infinite time, much the same would apply, infinite times over. If our universe simply keeps expanding at its current rate and its entropy keeps rising, then we would once again be left victim to quantum weirdness, as particles would pop in and out of existence. Though again statistically very unlikely, within infinite time, everything would happen infinitely often, from single particles appearing in the vacuum to entire brains, or more specifically, bodiless human brains drifting alone through space. These so-called Boltzmann brains are part of a grim thought experiment named for the late 19th century scientist Ludwig Boltzmann. It may seem vanishingly unlikely that the void of space could create a human brain, replete with thoughts and artificial sensations and memories, but due to the bizarreness of quantum fluctuations, it really is one of the permutations that an infinite universe can cycle through. Given enough time, this seemingly impossible permutation could spontaneously appear. And of course, given an even longer amount of timeless time, it could even happen over and over again. It follows that, statistically, our thoughts and experiences are much more likely to be an illusion of a fictitious universe conjured up by a non-corporeal Boltzmann brain than they are true reflections of the cosmos so close to its birth. Antonio Padilla also suggests that the universe may reach its Poincaré recurrence time after about 10 to the power of 10 to the power of 120 billion years. This would be the moment when statistically all the particles within a finite universe would repeat their initial arrangement, and so the cycle would begin again. And finally, we arrive to an endless universe of infinite size, which comes with its own challenges, chief among them, the measure problem. In a universe of infinite possibilities, each happening infinitely often, how can we ever calculate the probabilities or ratios of anything? How can we ever truly know the laws of a universe in which anything is possible and equally infinite? And so, in this sense, trying to use the observable universe as any kind of template for how the infinite beyond may function is a lost cause. We might imagine that the parts of the eternal universe that we can see may represent a very small percentage of the whole, but the nature of infinity is such that any fraction of it is essentially zero. All we have ever known, will ever know, or could ever hope to know would be exactly 0% of the infinite cosmos. Under such conditions, the very field of cosmology becomes meaningless. Predictions are impossible. Our theories about the Big Bang, the laws of nature, and the far future of our universe simply hold no water, because we know precisely nothing about the infinite cosmos from which it arose. The enigmas themselves are unknown, unknowable, and infinite in extent. Does that mean that our very lives are meaningless? It's not hard to see why the Greeks backed away from the concept of infinity and all it entailed. Some 2,000 years since they strove to reason themselves out of an infinitely deep chasm, we still find ourselves grappling with the same problems. Despite the development of transfinite mathematics, a better than ever characterization of what exactly is infinity, and every measure we can hope to conjure to study the potentially infinite cosmos on our doorstep, we really are no closer to understanding anything about this number beyond numbers. Confronting infinity means confronting an inescapable existential dilemma. But even this is not the end. Our own universe, infinite or not, is just the beginning when it comes to grappling with infinity in cosmological theories. There are many other, perhaps even more discomforting infinities lurking over their own impossible horizons. Infinities that dwell inside of us, infinities lingering in the distant past, and infinities bubbling endlessly inside larger infinities. Polish-born mathematician Benoit Mandelbrot was fascinated by the apparent chaos of the natural and man-made world, and sought to find order in everything from the fluctuations of the financial markets to the shape of a rocky coastline. And in 1958, moving to New York State, he found himself in the perfect place to pursue his curiosity. The IBM Research Center in Yorktown Heights had been created to help the computer company develop its hardware and software, as well as the new kind of mathematics that lay behind its computer systems. Mandelbrot ended up staying there for 35 years. But his work didn't focus on improving the computers. Rather, he demonstrated what the computers could do for the field of maths itself. And so in 1980, he was among the first to use computer graphics to visualize something that simply wouldn't be possible with just pen and paper. Using relatively simple equations, he managed to display a unique kind of geometry, which he referred to as fractal, after the Latin word for broken or shattered glass, and which is defined by its self-similar structure, independent of scale. This means that, regardless of the scale it's observed at, a fractal will always contain more detail. You can zoom in or out infinitely, without ever reaching a more simple geometry. Have infinite complexity. Mandelbrot showed this with his computer-generated Mandelbrot set, but he also observed how such fractals can be found in nature. Similar fractal, scale-independent geometry can be seen in the leaves of ferns, the head of Romanesque broccoli, even in the clustering of distant galaxies. Was the entire universe a fractal? Of course, we now know this is not the case in our observable universe. On the largest scales we can examine, homogeneity reigns. But could there be parallels on scales even larger? The question of how far the universe extends beyond our bubble may not be answerable right now, but even if we begin our cosmological studies with what we can see, it's not long before we bump against the concept of infinity once again. Our universe is expanding. Everything is moving away from everything else, growing like a loaf of bread in a warm oven. If it began from an infinite point, then our observable universe began as a finite part of that initial infinite point. And again, although our observable universe grows bigger and bigger, this is just a measurement of how far the light has traveled over time. The actual physical universe has just become less and less dense. Larger objects like us and galaxies are held together by gravity, but wherever we look across the cosmos bar our local group, every other galaxy is moving further and further away, at an average rate of 70 kilometers per second per megaparsec. Continue the trend of expansion into the far future, and what do we find? Unless some as yet invisible force comes into play, we can expect that space-time will continue to stretch, pushing every galaxy away from its neighbors, stars away from one another, and eventually leading to a universe-wide heat death. But despite this, there is no final event to bring the universe to a close. Our observable universe will keep expanding until it becomes infinitely large. And again, because of the nature of infinities, this will take an infinite amount of time. And yet counterintuitively, even if we had this infinite time, we could only ever explore a finite part of an infinite universe, as expansion would always be one step ahead. As we trace the universe back through its history, that expansion also reverses, and as we rewind the clock, the cosmos shrinks down, becoming smaller, denser, and hotter until it no longer resembles anything like the universe we know. The laws of physics begin to act in bizarre and unexpected ways, allowing cosmologists to make surprising conclusions about exactly how things began. The problem lies in actually identifying that starting point. We can only understand the universe once it reaches a size where our physical laws mean anything, which physicists recognize today as the moment when the cosmos was around 1 Planck length in diameter. According to the early 20th century physicist Max Planck's calculations, the eponymous Planck length measures a minuscule 1.6 times 10 to the minus 35 meters, a decillionth of a millimeter, and is about 1 billion trillion times smaller than an atomic nucleus. It is the size at which quantum uncertainty causes our known physics to break down. But the universe may well have been expanding prior to this, blooming outwards from a point that was infinitely small, infinitely dense, and infinitely hot. Of course, we have no idea what this might look like or how it might behave, but there's nothing in what we see and what we model to suggest there was any other kind of beginning. Of course, the nature of infinities means that, in order to compress the universe down to a primordial state that is infinitely small, it would take an infinite amount of time, which means that our observable universe may well be much, much older than the 13.8 billion years we calculate. Indeed, at the Big Bang, it may already have been infinitely old. And so, based on simple observations of how the universe is now, we cannot escape the unprovable, but as yet not disproven logic of unbounded expansion, both backwards and forwards in time. How then can we reconcile our models of the Big Bang and the inference of infinite smallness with the inescapable logic of infinite largeness? It's true that the observable universe is expanding right now, but that need not be the case for the entire infinite universe, or for all of infinite time. Cosmologists have suggested that our local universe, consisting of the parts we can see and an unknowable amount beyond, are regions of limited inflation within an immortal and infinite whole. This is the theory of eternal inflation, first mooted in 1979 by Alan Guth and given its eternal elements in the early 80s by Andre Linde, Andreas Albrecht, and Paul Steinhardt. We would therefore be one minuscule part of an eternal universe, where inflation may be always happening, but not necessarily always at the same time, in the same place, or to the same degree. And the logical implication of this is that our universe is one of infinitely many bubble universes that have spontaneously germinated and bloomed from the endless whole. Each of these corners of the infinite multiverse may sit at different stages of cosmological development and may be ruled by physical laws very different to our own. But they will forever be beyond our grasp, separated by the uncrossable gulf of infinite space. And so exploring the patchwork world of multiverse theories opens up a further Pandora's box of infinities. In order to accommodate the exotic physics that the infinitely small requires, many physicists delve into the world of possibilities offered by various string theories and M theory. In this theory, it is claimed that our reality exists as a fleeting intersection of dimensions, and that many such juxtapositions might exist simultaneously and pass in and out of existence as the larger bulk of hyperspace transforms. So we must contemplate not only the notion of infinite universes in our 3 dimensions of space, but also the existence of a multiverse made from any number of dimensional combinations. And again, there is nothing to say that these different universes would have the same laws of physics as our own, which of course opens up a whole new frontier of infinite options. Different strengths of gravity, different masses of fundamental particles, truly endless possibilities. Our Big Bang may be the smallest scale that we can resolve, and the ultimate heat death of the universe may be the largest, but if some omnipotent bodiless power were able to zoom in or out of our expanding bubble, they might find it to be just a single layer of complexity in a larger whole. And indeed, one more idea is very close to this. Robert Penrose's conformal cyclic cosmology. When, from our perspective, our own bubble has become infinitely large, it may simply be the seed for a new, infinitely small Big Bang, marking the beginning of a universe on an entirely different scale. But though alluring, these are just theories, and as with much of the challenge of real infinities, they are incredibly difficult, if not impossible, to prove. And so perhaps that is what can save us from these existential crises, the simple fact that the very nature of infinity means that we could never have real evidence for an infinite cosmos. All scientists can do is continue to search for evidence of finite size. Keep following the turtles all the way down. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time.